Welcome back to Mr. Vaughn's classroom. Before we get started, I'd like to ask you to please hit the subscribe button, give this video a thumbs up, and leave a comment below. Today, we're looking at Unit 5, Introduction to Exponential Functions, Lesson 18, Expressed in Different Ways. The learning goal today is to write exponential expressions in different ways. We have two learning targets. You want to keep these in the back of your mind as we go through the practice problems, and at the end of the video we'll come back and review them. If at the end of the video you have any questions about these, please leave a comment below and I'll get back to you with any assistance I can offer. Learning target number 1 says that you can solve problems using exponential expressions written in different ways. And learning target number 2 says that you can write equivalent expressions to represent situations that involve repeated percent increase or decrease. And we have one glossary term, and that is growth rate. In an exponential function, the growth rate is the fraction or percentage of the output that gets added every time the input is increased by 1. If the growth rate is 20%, then 20% is 0.2, so the growth factor would be 1.2, because the 1 is maintaining the current amount, and the 0.2 is what's being added each time. Now we can begin the practice problems. The first practice problem says for each growth rate, find the associated growth factor. So a couple of things we need to make sure you understand first. The starting point is going to be 100%. That will be your initial amount. So 100% maintains that starting amount. Now, changing from percentage to a decimal, which is what we're going to be doing in these problems, you need to move the decimal point two spots left. So, let's look at our problems. In number 1, we have a 30% increase. That means we're going to take the original 100%, we're going to add the 30% increase, and that's going to give us 130%. But we need to write this as a decimal. So we're going to take 130. The decimal point would be right here. We're going to move that 2 spots to the left, and this becomes 1.30. So that is the growth factor. You would multiply each time by 1.3. Number 2. Now we have a 30% decrease. So we take the original 100%, but this time we subtract 30%. This leaves us with 70%. So now the decimal point would be right here. I need to move that 2 spots to the left and this becomes a growth factor of 0.7. Number 3, we have a 2% increase. So we have the original 100%, we add 2%, and that gives us 102%. Well, the decimal would be after the 2, so I'm going to move it 2 spots to the left, and my growth factor is going to become 1.02. Number 4, we have a 2% decrease. So we have our original 100%. This time we're going to subtract 2%, and that leaves us with 98%. Well, the decimal would be after the 8, so we're going to move it 2 spots to the left, and our growth factor becomes 0.98. Number 5, we have a 0.04% increase. We take the original 100%, we add 0.04%, and that gives us 100.04%. We're going to take that decimal and we're going to move it 2 spots to the left. So our growth factor is going to be 1.0004. Number 6, this time we have 0.04% decrease. So we start with our original 100%, we subtract 0.04%, and that leaves us with 99.96%. We're going to move that decimal point 2 spots to the left, and the growth factor becomes 0.9996. And lastly, number 7, we have a 100% increase. So we start with the original 100%, we add the 100% increase, and that gives us 200%. The decimal point would be after the 200, so we're going to move it 2 spots to the left, and the growth factor becomes 2. If you have any questions about how to write the growth rate based off of a percentage increase or a percentage decrease, then please leave a comment below and I'll get back to you with any help I can offer. Our next practice problem says that in 1990, the population P of India was about 870.5 million people. By 1995, there were about 960.9 million people. The equation P equals 870.5 times 1.021 to the power of t approximates the number of people in millions in terms of the number of years t since 1990. Number 1 wants to know, by what factor does the number of people grow in 1 year? So they're asking for the growth factor. And the growth factor is the number that has the exponent with it. So if they're asking for the factor, that's this number right here. So that means it's growing by a factor of 1.021 each year. Number 2, if d is time in decades, write an equation expressing the number of people in millions, p, in terms of decades, d, since 1990. So you need to understand that decades equals 10 years. So if I wanted to replace t as my exponent, then I would need to take the number of decades, multiply that by 10, and that would give me the number of years. So now what I can do for number 2 is I'm going to use this equation from the word problem. P equals 870.5 times the growth factor of 1.021 to the power of d times 10. Or, to write that more correctly, 10d. So now if I said it was 1 decade, I would multiply 1 times 10, and it would be 10 years. So this is the equation that would represent it using decades as the input instead of years as the input. Number 3, use the model that we originally had where the input is the time in years. And they want us to predict the number of people in India in 2015. So if I want 2015, and the model was created for 1990, then that is a total difference of 25 years. So for number 3, we're going to say P equals 870.5 times the growth factor of 1.021 to the power of 25. So in a calculator, you're going to say 1.021. You're going to use this button right here that shows x to the power of y. And you should see this little upward pointing arrow. And you're going to tell it that your exponent is 25. And then hit equals. This decimal, 1.68, is representing the growth factor multiplied by itself 25 times. Now you're going to take that and multiply it by the original 870.5 and hit equals. So this gives us 1,463 million. Because remember, we're measuring in millions of people. So now number 4. In 2015, the population of India was 1,311 million. How does this compare with the predicted number? Well, the predicted number was higher. So if we wanted to know how much higher, we can take the predicted value, 1,463, and subtract the actual 1,311. So it was 152 million people lower than the predicted number. So that means the growth rate after 1990 ended up being a little bit lower than it was before 1990. If you have any questions about any part of this practice problem, then please leave a comment below and I'll get back with any help I can offer. Our next practice problem says an investor paid $156,000 for a condominium in Texas in 2008. The value of the homes in the neighborhood have been appreciating by about 12% annually. Select all the expressions that could be used to calculate the value of the house in dollars after T years. So there's a vocabulary word here that you might not know, and that is appreciating. And this means going up in value. So it's increasing by the 12% annually. So if we look at A is taking the starting amount times 0.12 to the power of t. This is multiplying by 12%. That is a decrease of 88% annually. That is not what we're looking for, so A is incorrect. Choice B. The $156,000 starting value times 1.12. This maintains initial amount and adds 12% annually. That's what we're looking for, so B is correct. Choice C. We have the $156,000 initial price multiplied by 1 plus 0.12. This is the exact same thing we had in B. This part right here is the same as this part right here. And if B was correct, then that means C is also correct. It maintains the initial amount with the 1, and it adds the 12% annually with the plus 0.12. Choice D. We have the $156,000 initial price multiplied by 1 minus 0.12. This is a 12% decrease annually. It actually multiplies by 88%. So D is incorrect. And the final choice, E, the $156,000 initial price times 1 plus the 12% divided over 12 months. So this is applying 1% increase monthly for 12 months. The problem is, if we put that in a calculator, the 0.12 divided by 12 would result in 0.01. So the overall factor would be 1.01. If I raise that to the power of 12, then I end up with an effective rate of 1.127. Which is a 12.7% annual increase. So E is also wrong. If you have any questions about any part of this practice problem, please leave a comment below and I'll get back to you with any help I can offer. Our next practice problem says a credit card has a nominal annual interest rate of 18%, and interest is compounded monthly. The card holder uses the card to make a $30 purchase. Which expression represents the balance on the card after 5 years in dollars assuming no further charges or payments are made. So, a few things we need to make sure you understand. Nominal annual interest rate means that you take the interest rate of 18% and you divide that over the 12 months. And then you compound it monthly. So what we want to do is look and see what each of these actually means. A says we have the $30 initial times 1 plus 18. Well, the 19 means that we have 1900%. So this is yearly increase of 1800% effective. So that is not what we're looking for. Choice B. We have 1 plus 0.18. So this is an increase of 18% annually, but that is 18% effective, or this is 18% increase for 5 months. So it's not the right percentage because it's effective and they're doing it every month for 5 months. We want it monthly for an entire year for 5 years. So B is wrong. Choice C. Here we get a little bit closer. This is 18% divided by 12. So this gets us the nominal interest rate. But it only does it for 5 months. So each time we're getting a little bit closer to what we're really supposed to have. D is the one that does it correctly. Here, they take the 18%, they divide it by the 12 months so that we get 18% nominal annual interest. And then they take the 5 years and they multiply it by the 12 months so that we get the 60 months of compounded interest. So this would be the correct way to represent this situation. And if you were curious as to how much that is, we can take the 0.18, divide it by 12, add the 1, And now we're going to take this to the power. 5 times 12 is 60. And now we multiply this by the original $30 purchase. And you would actually owe $73.30 on that original $30 purchase. If you have any questions about any part of this practice problem, please leave a comment below and I'll get back to you with any help I can offer. Our next practice problem is the last practice problem for this lesson. The expression 1,500 times 1.85 to the power of 3 represents an account balance in dollars after 3 years with an initial deposit of $1,500. The account pays 8.5% interest compounded annually for 3 years. Number 1, explain how the expression would change if the bank had compounded the interest quarterly for 3 years. So if we are compounding quarterly instead of annually, the first thing we need to do is divide the 8.5% annual interest by 4 quarters to get nominal annual interest. The next thing we need to do is multiply the 3 years by 4 quarters to get total compounds. And now number 2 wants us to write a new expression to represent the account balance in dollars if interest is compounded quarterly. So all we're going to do is take the steps that we just described in number 1 to rewrite the expression from the word problem. So we're still going to have the initial $1,500, but now it's going to be 1 to maintain the current amount plus the 0.085 divided by the 4 quarters to the power of the 3 years times 4 quarters. So this would be 1,500 times 1 plus 0.085 divided by 4 to the power of 12. And this would represent the quarterly compound interest. And just in case you wondered about the difference, originally we had 1.085 to the power of 3 times the original 1,500 and that would give us $1,915.93. Original. Now, if we tried the quarterly, we would have the 0.085 divided by 4 plus 1 to the power of 12 times the original 1,500. It would be $1,930.53 if it was compounded quarterly. So you would actually make about just under $15 extra if they would compound it quarterly for you. If you have any questions about how to solve this practice problem or any of the other practice problems in this lesson, please leave a comment below and I'll get back to you with any help I can offer you. Now, before we finish this lesson, let's go back and take a look at the learning targets again, just to make sure you understand everything you needed to. So to finish up, we had 2 learning targets in this lesson. Number 1 says that you can solve problems using exponential expressions written in different ways. As we worked through the practice problems, we looked at writing percent increases, percent decreases. We looked at annual percentages. We looked at effective annual percentages when they were compounded monthly or quarterly. These are all different ways that you can write exponential equations. Learning target number 2 said that you can write equivalent expressions to represent situations that involve repeated percent increase or decrease. So you looked at ways of writing it where you combined the 1 to maintain the current, and then the adding or subtracting of the percentage increase or decrease. You looked at ways to write it where you just wrote the result of that increase or decrease. You looked at ways of writing them where you were compounding monthly or quarterly instead of annually. These are all equivalent ways to write the same information. If you feel comfortable making these 2 statements, then you're right where you should be. If you still need help with either of these, please leave a comment below and I'll get back to you with any help that I can offer. If you found this video helpful, I simply ask that you please subscribe, give this video a thumbs up, and engage in the comments. I look forward to seeing you in the next lesson.